Okay, let's go ahead and get started. So today we're going to be talking about something called antiderivatives. Oop. So the idea behind this is, let's say, for some reason you know the rate of change of a quantity, and you want to know a function for that quantity. So for example, like water might be emptying from a tank and you know the rate of change of water coming out of the tank. And so are you able to, from that information, tell how much water is still in the tank at the time t? Or like another example, if Bean is running after a stick and we know how fast he's running, can I give you a function that tells you his position in terms of time just from the information of the rate of change? And to do this, we'll be doing something called antiderivatives. And basically what this is we're going to reverse the process of taking the derivative of a function. So we've gotten a lot of practice with, like, if you have a function, you can just take its derivative. And so now we'll be looking at like an f prime and trying to figure out what a possible f might have been. So so I'll just say, I'll write something. So I'll say, like, given an f prime, how do we find f? And also, I guess there's a question of how many possible f's might there be and what could they look like? So here's the definition. And usually instead of, so we'll usually use lowercase f to denote the function that we want to take the antiderivative of, and then capital F will be the function where capital F is equal to f prime. So a function capital F is called an antiderivative of the function little f on an interval I if the following thing holds. So if we take the derivative of capital F, so capital F prime of x, if this is equal to little f of x for all x's coming from that interval. Okay, does the definition make sense? So typically you'll be given the little f and you would be asked to figure out what the corresponding capital F is, such that when you take the derivative of capital F, you get little f. So here's an example. Maybe I'll pause also and say, like, in general, finding an antiderivative can be quite hard. So when we're taking derivatives, the process is like more or less algorithmic. Like if I give you a function, you will most likely be able to just use the rules that you have to figure out what the derivative is. But taking the antiderivative is a lot messier and a lot more challenging. So to see why this might be the case is, like, for example, the product rule, right? That output is a little bit complicated. And so recognizing that that output is the derivative of a product is, like, kind of difficult. And same thing with chain rule, like recognizing something as being the output of the chain rule is a little bit hard. So for the most part, like, those more advanced techniques will be covered in your next course, which will be 1301. But we can reverse some of the rules that we know already pretty easily. So for example, let's find the antiderivative of, or an antiderivative of this function. So let's take little f of x to be x squared, and we'll find an antiderivative. Okay, so what is f? What is capital F going to be? So let's think about this. When I take the derivative of something, when is my answer a polynomial? What type of function has as its derivative a polynomial? Yeah, it's also going to be a polynomial. And what will the degree of that polynomial be? Yeah, it'll be one, right, so if I take the derivative of a degree n polynomial, I get a degree n minus 1 polynomial, right? So the degree goes down by 1 when you take the derivative. So if I want to reverse that process, the degree is going to go up by 1. So like maybe a reasonable guess is that f should be x cubed. So let's see what happens when I take the derivative of this. So if I do f prime of x, I get 3x squared. Okay, so this is close, but I have a coefficient here that I didn't want here. So, and that just comes from, you know, when I do the power rule, I have to multiply by 3 out front. So what I'll do is I'll just modify my guess. And so I'll add a factor of 1/3 out front here. So that's what we wanted. Okay, so my antiderivative is 1/3 x cubed. Does that sort of make sense? Can anyone think of another antiderivative? Yeah. Yeah, so if I added any constant to this, so notice I'll just add like 7 or something. So this is also an antiderivative. And that's just because when I take the derivative of this, the derivative of the constant will be 0, so that factor will go away. Okay, are there questions about this? So we're gonna make, I'll make a general statement that sort of explains this feature. So let's recall, so this was from before spring break. We used the mean value theorem to prove a fact, which was that, so we proved using MVT that whenever two functions have the same derivative, they differ by a constant. Does this sound familiar? So if two functions have the same derivative, they differ by a constant. This is something we proved a few weeks ago. And so how is this helpful in this setting? So let's say, so if capital F and capital G are both antiderivatives of a function f, then what that means is, so in symbols, we would have f prime of x equals f of x, and also g prime of x equals f of x. And so that means that, going back to this statement, these two functions have the same derivative, so they must differ by a constant. Okay, so what that means is that f of x minus g of x is equal to some constant c. So c is just some real number. And just rearranging this, we get that g of x, or maybe I'll write it like this. So we get that f of x is equal to g of x plus a constant. Does that make sense? Other questions? Okay, so this, let me just summarize this in a theorem. So by what we've just written here, we get the following theorem. So if f is any antiderivative of little f on an interval I, then all the antiderivatives of f on I are of the form f of x plus some constant. So in the example that we found where we took the antiderivative of x squared, all of the antiderivatives of x squared look like 1/3 x cubed plus any number you like. So this is called, this f of x plus c, this is called the general antiderivative. Just because it kind of summarizes all of the possible options in one expression. So you will often see like 1/3 x cubed plus c as like the general antiderivative. And then the choice of f, so this guy, is referred to as a particular antiderivative. Maybe I'll just write down the example. So in our example, the general antiderivative of x squared is 1/3 x cubed plus c. Okay, are there questions? Okay, I'm gonna give you all a few minutes to work out some examples. So here's some problems. So you're gonna find the general antiderivative for the following functions. So let's do sine x, x to the n when n is greater than or equal to 0. Let's just do those two. So I'll give you a few minutes to think about those and then we'll discuss together. Still thinking, or you want to discuss the answers? Ready? Okay, sounds good. So what is the general antiderivative for sine x? Yeah. Yeah, so this one's going to be minus cosine x plus c, right? Because when you take the derivative of cosine, you get minus sine, and so you have to multiply this by -1. And then what about for 2? What is the general antiderivative for x to the n? Yeah. Yes. So this is 1 over n plus 1, x to the n plus 1 plus c. Yeah, good. So when we take the derivative of this, the good thing about this is that you can always check your work, right? So if you write something down, you can then take the derivative and hopefully you'll get the thing that you started with. So we take the derivative of this, we will take the exponent down and cancel this coefficient, and then we'll be left with x to the n. So this works out. Okay, are there questions? So let me write down some antiderivative formulas just that come from reversing the derivative formulas that we have. Okay, so basically this is just going to be derivative formulas in reverse, and they give you an antiderivative formula. So the easiest one is the constant multiple. So I'll write a function in this column and then its antiderivative here. So let's just suppose as input that f and g are functions with capital F and capital G as their antiderivatives. Okay, so if I have something like c times f of x, then the antiderivative is just going to be c times capital F of x. And then for the sum, we get a sum rule. So if I have f of x plus g of x, then that's just going to be capital F of x plus capital G of x. Right, and the proofs of these are just the fact that we know if I take the derivative of this whole thing, we have a sum rule for taking derivatives. So that's just going to be the derivative of this plus the derivative of this, which is this expression. Okay, so we have that. The power rule we already wrote down. And this actually works for any n not equal to 1. So if I have x to the n, then its antiderivative will be x to the n plus 1 divided by n plus 1. So why does this not work when n is equal to 1? Sorry, minus 1. Should say minus 1. Do I ever get 1 over x as the derivative of something of the form x to the some number? No, right? Did I take n, let's say greater than or equal to 0? I'm always just so okay. So if I take the derivative, let me write down a little bit to justify this. So we know that the derivative of x to the n. So if I take the derivative of that, this is n times x to the n minus 1. Okay, so if I wanted this to be minus 1, right, that would mean that n was 0, but then this would just be 1, and the derivative of 1 is 0, right? So it's not possible to get x to the negative 1 as an output of taking the derivative of something that looks like this. So reversing that for the antiderivative rule, we cannot have n equals -1 here. Okay, are there questions about that? Maybe I shouldn't have erased this. Okay, and then here's a bunch of trig rules. So if I have cosine x, the antiderivative is going to be sine x. And then as we saw in the example, sine x is minus cosine x. And then the other ones are a little bit messier, right? So if I have secant squared x, then I get tan x. And if I have secant tangent, I get secant. And if you wanted to take the antiderivative of, say, tan x or secant x, this requires more sophisticated techniques than we're going to cover in this course. So this is, you're gonna need to put in a little bit of work to figure out what those would be. Okay, so that's all of the antiderivative formulas that we are gonna have. Are there questions before we use some examples?
Can you go back up to the antiderivative of the sum?
Yes. Okay, so let's do an example. So let's find the general antiderivative for this function g of x, which is 4 sine x plus 2x to the fourth. Okay, so using the rules that we had, basically I just need to break this up into smaller things that I can individually take the antiderivatives of. So we know that the antiderivative of a sum of two things is the sum of antiderivative of this one plus antiderivative of this one. And then again, we also have a constant multiple rule. So the antiderivative of this is just going to be 4 times the antiderivative of sine x, which we know. And then we'll do a similar thing for this half of it. So let me just find the antiderivative of these two sort of like constituent functions. And then we'll use those two antiderivatives to build back up the antiderivative of g. Okay, so we know antiderivative of sine x is minus cosine x. And antiderivative of x to the fourth is going to be x to the fifth divided by 5. So this is by trig and power rules. Okay, so then that means that, so then to get the antiderivative of g, we just have to put this all together. So the antiderivative, or let me say an antiderivative for g is, and I'll call this function capital G of x. So it'll be 4 times minus cosine x plus 2 times x to the 5th divided by 5. And then just simplifying this, so this will be minus 4 cosine x plus 2/5 x to the 5th. So then the general antiderivative would just be, all I need to do is add any constant to this. Are there questions? Is this making sense? So the sum and constant multiple rules work exactly as you would hope, but the product rule does not work, right? So maybe we'll just do an experiment to see that it doesn't work. So maybe doing this with like a polynomial is the easiest way to see it, but we could do any function. So maybe I'll just start with, like, if I take f of x to be, let's say x to the 4th. So we know the antiderivative should be x to the 5th divided by 5, right? But what if I decided to view f of x as x squared times x squared? Okay, so let's pretend for the moment that we live in a different universe and we have a straightforward product rule. So meaning I can just individually antiderivative each of these factors and then multiply them. And let's see what we get. So the antiderivative of x squared is x cubed divided by 3, right? Same thing here. So then in my alternate universe, f of x would be x to the 6th divided by 9. Right, so this is just a demonstration of the fact that f of x, g of x does not have f of x times capital F of x times capital G of x as its antiderivative. Because these two things do not equal each other, right? And additionally, I can take the derivative of this thing and see that I don't get the right answer. So if I take the derivative of this, that's going to be 6 over 9 x to the 5th, which is not x to the 4th. Does that make sense? Okay, so let's do another Are there other questions about this or the previous example? I'll do another example. So one thing that you can do is if you have a little bit more information about your antiderivative, then you can actually figure out what the constant needs to be. So this happens a lot in applications because, for example, so going back to the bean fetch example, maybe I know bean's initial position when I throw the stick, and I know his speed. And using that, that's enough information to determine his position. So here's like an example of how something like that might look. So we'll find f if I know that f prime of x is equal to x times the square root of x. And I also know f of 1 is equal to 2. Okay, so this like extra bit of information is often called an initial condition. And we will be able to use this to figure out what the constant c has to be. So, okay, how can we find the antiderivative of this? Yeah. Yeah. So that actually, okay, so that is a technique that is used and it'll come up in 1301. But we can do something a little bit simpler here. So you can just do you don't want to say it? Okay. So you can just rewrite all of this as x to the something, right? And then use the power rule. So, because this is x to the 1/2, and then we'll just combine them to get x to the 3/2. So let's just note that we can rewrite f prime as x to the 3/2. And then I'll use the power rule. So by the power rule, I get that the general antiderivative is, okay, so adding 1 to 3/2 gets 5/2, right? And then we also need to divide by that number. So we get x to the 5/2 divided by 5/2 plus c. So I'll just sort of rewrite the denominator. So we get 2/5 x to the 5/2 plus c for our general antiderivative. Okay, are there questions up to this point? So then what I'll do is I'll plug in f of 1 equals 2 and then solve for c to figure out what c has to be. So then it's like, so here we'll solve for c using f of 1 equals 2. So we know that 2 has to be equal to 2/5 times 1 to the 5/2 plus c. So 2 is equal to 2/5 plus c. So that means that C is equal to, so 2 is actually 10/5, and then we're subtracting 2/5, so we get 8/5. So that means that, okay, so our problem asked us to find F if given this information. So we know now that F of X is equal to 2/5 X to the 5/2. So I'm just copying down from here from our antiderivative. And then now we also know what this constant C has to be. So plus 8/5. Okay, does that make sense? So you could keep going. I think in the web work, there might be one where you're given the second derivative and then like 2 pieces of information. And then you can solve for F. So like if you think about it, if you had the second derivative, you would add a constant each time you antiderivative, and so then you would have 2 constants that you have to figure out, and so you have 2 pieces of information to solve for those constants. Other questions? All right, I'm gonna give you guys some examples to practice with. So here's some problems. So find F in each of these cases. So the first one is you're given that F double prime of X is equal to 4x cubed plus 24x minus 1. Second one, F prime of X is equal to 5x to the 2/3. And then last one, F prime of X is equal to x plus 1 over square root x, and f of 1 is equal to 5. And maybe I'll just say find any f that satisfies this. Okay, so I'll just give you time to work on this until the end of class, and if you have questions, just raise your hand and I can come around and answer.
The second constant to, you take the antiderivative once, and it'll be plus C, and then you do it again, plus another letter.
Yeah, you could use D or something, yeah. Or you could call them like C1 and C2. Okay, so class is over, so you can go, but if you have questions about the problems, feel free to ask me on your way out.